Exponential functions are functions that grow or decay based on the previous amount. Classic examples of exponential growth are compounding interest, population growth, radioactive decay, and so on. Simple exponential functions are of this form right here. F of x equals b to the power of x. B is called the base, and the x is the variable in the power, the exponent. So we'll say exponent here. This has the variable. Now this should not be confused with a function that looks like this. In this case, the base has the variable, and the power, the exponent, is just a number. So just like in exponential functions, the base is a number. In this function down here, the power is the number. So one function, the exponential functions, has the variable in the exponent. The other function has the variable in the base. These functions are called polynomials. All right, what do exponential functions look like? Well, we can create a table of values. For instance, let's look at this exponential function here. We can create a table of values quite simply by just choosing 5 points. We'll do -2, -1, 0, 1, and 2, and plugging them into our function. We get 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 1, and 2 to the 2. And then that gives us 2 to the -2. The negative power flips it. We have 1/2 squared, the same thing as 1/2 squared. That's what the negative does. And 1/2 squared is 1/2 times 1/2, which is 1/4. The negative again flips it, and now we have 1/2 to the power of 1, but that's just 1/2. Anything to the power of 0 is 1. 2 to the 1 is 2, and 2 squared is 4. So let's plot these points. We have -2, -1, 0. That's the origin. 1 and 2. Then I'm going to go 1 here. Give myself enough room. 2, 3, 4. So -2 goes to 1/4. Right here is 1/2. There's 1/4. So that's going to be right about there. -1 goes to 1/2. 0 goes to 1. 1 goes to 2. And 2 goes to 4. Drawing a smooth curve between these. Looks like that. And what you'll see is that this one actually goes off this way. That's the basic idea of what an exponential function does. Any exponential function of b to the power of x, as long as b is greater than 1, if that's the case, it's going to look very similar to this graph. How it shifts and things is just minor details, but it's going to look very similar to this. All right, let's look at another one. Let's look at f of x equal to 1/2 to the power of x. And we'll create a table of values for this, again, using the same numbers that we used last time. So -2, -1, 0, 1, and 2. And so here I've just gotten them plugged in to our functions here. The negative flips it. We get 2 over 1 squared. And 2 over 1 squared is the same thing as 2 squared, which is 4. 1 over 2 to the -1/2, or to the negative power, gives us this, but that's the same thing as just 2. This is always equal to 1. 1/2 to the 1 power, that's just 1/2. And 1/2 squared is 1/2 times 1/2, which is 1/4. You see, these numbers are very similar to the numbers we had before, right? The ones we had before was 1/4, 1/2, 1, 2, and 4. These numbers are 4, 2, 1, 1/2, and 1/4. They're kind of flipped. And so if we graph this, using the same kind of graph I did before, we get -2 goes to 4, -1 goes to 2, not 3, goes to 1, to 1/2, and then 1/4, about right there. It looks like that. And this is just the flipped version of this one. Now, let's look real quick at this value here, or this function here. Let's look at the table of values. So let's say we have, again, the same 5 that we've been using. Now we have 2 to the power of negative 2. But 2 to the power of negative 2 is positive 2. And that gives you 4. 2 to the power of negative 1, that gives you positive 1, which gives you just 2. 2 to the power of -0, well, negative times 0 is 0, and 2 to the power of 0 is 1. 2 to the power of -1, that just flips it, you get 1/2. And 2 to the power of -2 gives you 1/4. You flip it and you square it. And this is the same as this. These are the exact same functions. And that's just because of rules of exponents. Namely, 1/2 x, right? If we flip this, 2 over 1 to the -1 to the x. All I've done here is I've just taken the inside portion and flipped it. And you can flip it by giving it a negative power. If you do flip it, then you have to give it a negative power. If it doesn't already have one. But this can be 2 over 1 is the same thing as 2. And a power to a power, multiply the powers. -1 times x is -x. So you see directly here that 1/2 x, 1/2 to the power of x is the same as 2 to the -x. Okay, real quick, let's look at the domain, range, and the intercepts. Just some basic function analysis here. So the domain for this one, it looks to be from -infinity to +infinity. The range here is interesting. If you actually zoomed like on this way and kept going and you kept going, it never crosses the x-axis. So but it does get infinitely close to it. It's what's called an asymptote. And that means that it goes up to 0, but it does not include 0. And then it does in fact go on towards +infinity this direction, right? So that's also included. Okay, y-intercept. There's a y-intercept right there at 0, 1. X-intercept. Well, I just told you the range never crosses the x-axis, which means there is no x-intercept. Increasing, decreasing, constant. This is always increasing. It's increasing on its entire domain. So decreasing and constant, there are no intervals of that. And there is no symmetry here. Now, looking at this function here, the f of x equals 1/2 x, or which is the same thing as 2 to the -x. All of the values are the same. The domain, the range, the y-intercept, the x-intercept, except this is decreasing on the entirety of its domain. That's the only difference here. Here we are once again using Desmos to graph these things. The red line is the first graph I made, which is 2 to the power of x. And the blue line here is the second graph, which is 1/2 power of x. You can see here at the top two. You see how this red line just shoots up, and actually as you go up, it goes more and more and up. One thing I didn't say is that this does actually end up continually going this way. You can see that by changing the range of values. Eventually, it will always hit every single x value here, right? We can zoom out quite a ways. It looks like it just shoots up like that. But if we change the max y value to like 1,000, like eventually, it takes a very long time. You see how it does actually start going out and out and out. And you can do that as many times as you want. You can keep zooming out, and you can keep increasing the y value, and it will keep continually going out. It's just like the polynomial function that I showed you. It has the same behavior, but this function, the exponential function, takes a lot longer to get over to every single value, but it does in fact go there. It just takes quite a while. Okay, and this 1/2 x is the exact same thing. And then for both of these, you can see here that this line gets very, very close. It looks like it's the same thing as the, but there you go. It's not the same thing as the intercept. I had to zoom in quite a ways to show that. And as you keep going more and more on, to the left, this will get closer and closer. It's getting slowly and slowly closer. And it'll always get closer and closer. It will never cross it. It's called an asymptote. An asymptote is one that gets continually closer to some point. It gets infinitely close to it, but it never ever crosses it. That's what this thing has. So this is the basic exponential function. This every single function, simple b to the power of x, has this shape. You can see 10 to the power of x. Very similar shape. It's a little bit different, right? But it's got the same shape. It's asymptotes on the left-hand side, and then shoots off towards infinity on the right-hand side. E to the power of x is arguably the most important function there. Let me give it a different color here. Blue. Has similar behavior here. It's asymptotes on this side, hits 1 here, and then goes on up that way. It always hits 1 because b to the power of 0, no matter what b is 1. Pi to the power of x, this is going to be the same thing because pi is just a number. It's 3.1415 and continues on. You can't see it. Let me just different color here. What's this purple line here? And then 1,000 to the power of x, you see how that one's a lot sharper. In the orange, it's a lot sharper. That's because 1,000 is a very big number, and so it shoots off towards infinity much faster, and it gets closer to 0 much quicker on this side. That's how it works. But all this has the same behavior. Asymptotes to 0 on this side, shoots off towards infinity on the right-hand side. Now, 0.01, this is different in that, let me go back to, I'll leave 10 on there. This is different in that it's now flipped, just like the 1/2 was. So it goes up to infinity on the left-hand side now, and goes off to 0 on the right-hand side. That's the differences there. Okay, now let's talk about function transformations. This right here is the function transformation general form. A times the function, which on the inside of the function is b times the variable, minus c plus d. Each one of these things has a specified value. I talked about this in section 2.5. But a and b are multipliers, so they're going to either stretch or shrink vertically or horizontally. because they're multiplying. And C and D are adders, and so they're going to shift it either horizontally or vertically. So because I showed you that each base here results in a different type of function. It's the same behavior, but a different function. The base is important. I'm choosing to show you the function transformations using base 2, just because I think it looks nicer. But all of these have similar behavior, but they are different. Okay, just keep that in mind when you're working with exponential functions. Okay, so this is our basic function. It's just the same thing as 2 to the power of x. They both are fitting on that one line. And now a, let me zoom out a little bit. A stretches it horizontally. If it's negative, it flips it and then stretches it horizontally downward. On the left-hand side, it's hard to see that stretch. That's because there's kind of like this anchor point. The anchor point is really off towards negative infinity. It's going to be at 0. So it always has to go there. But you can see on the right-hand side, it's being pulled upward. Imagine putting your hand up here and pulling this function upward. That's what happens when you give it a higher value of a. It's being stretched upward. And when you give it a value that's smaller, you're kind of squashing it downward. See how it's getting squashed? So imagine putting your hand up here and just pushing down on it. It's getting squashed downward. So it's being compressed vertically and being stretched vertically. The flipped is being compressed. This would be -1. And then it gets compressed after it gets flipped and gets stretched after it gets flipped. That's what the negative does. That's what A is. B, A is a stretch and compress vertically. B is the same horizontally though. When B is high values, it gets compressed now horizontally rather than stretched horizontally. It's being like, imagine putting your hand on this side and on this side and squeezing them together. That's what's happening here. It's getting compressed more and more and more and more. And then when you have something that's less than 1, you have a stretch. So you're pulling it apart. It's getting stretched until it just goes to be a flat line at 0. You stretched it completely. What's interesting is that if you put 0 into there, you see how it does not asymptote. In fact, this is a constant. That's because b times if b is 0, b times x is 0, and now there's no more variable in this. It's just a number. And it's going to equal 1. The way I have this set up, but that's what b does. It's a compression greater than 1, a stretch less than 1, and the negative is just a flipped. And you can see here, when b is -1, that's the same thing as this 1/2 x. And I showed you that algebraically. Okay, let's look at C and D. These should be straightforward. C is on the inside, so it's going to be a horizontal shift. If C is positive, making this a negative, in this case, it'd be -4 on the inside. That's going to be a shift to the right. If C is negative, it's going to be a shift to the left. It's just a straight shift. There's no compression or stretching. It's just a shift. D is a shift up and down. What's kind of interesting about D is that it actually changes the asymptote. The way I have it here, I have D equal to 5. The asymptote is now at 5. It's going to get closer and closer to 5, but never cross it. That's because I shifted it upward. I'm just moving to the left here. I shifted it upward. And that's how the asymptote shifts. The domain, however, is always everything. All right, let's look at e to the power of x and e to the power of 2x plus 3. What is this new function going to look like on our graph here? So e to the power of x looks like this. And e to the power of 2x plus 3. Well, this plus 3 is adding on the outside of the function. It's just like this plus d here. So we should know that this plus 3 is going to be a shift horizontally, or sorry, not horizontally, vertically. So this point really should be just moved up 3 units. So it should go right there at 4. Okay, now this 2, you can see this is multiplying the x, so it looks like this b here. Okay, and that b, you remember, is a compression or a stretch horizontally. Because b is greater than 2, I can show you on this one again. This is the original function here for 2 to the power of x, right? If b increases, it's being compressed horizontally. And so you see, if I put it on 2, if I can get it there, it's compressed more than just its original function. So this is the original 2 to the power of x. This is the power of 2 to the power of 2x. So it's being compressed inward. So the same thing should happen here. This should be compressed inward. And so it should be shifted up and compressed inward. It should be shifted up 3 units to here, and this should really be compressed inward. And that's in fact what it looks like. If I were to shift this other one up, you see how this is compressed, and the black is compressed inward from the purple. But that's if it's shifted up. That's the transformations there, and that's what it should look like. So probably one of the most amazing simple functions in mathematics is this function right here. F of x equals e to the power of x. E, this base here, e, is called Euler's number. This is named after Leonhard Euler, a mathematician in the 1700s. He was probably one of the most prolific mathematicians ever. He's attributed to starting so many different fields of mathematics. He even wrote a lot of papers. I think he actually wrote more papers than he did before he was blind. After that he was blind, he used to just like visualize the mathematics and speak it out and have people write down what he was visualizing. And he proved a lot of things after he was blind. E is approximately equal to 2. I'll just give you the longer number, 8281827, but you can use it as like 2.72. And a very interesting property of E, and probably what makes it so interesting, is that if we take 1 plus 1 over n, power of n, and we put bigger and bigger values of n in there. So what we're saying there is we're taking the limit, this is a calculus notation, as n goes to infinity. So you're just putting bigger and bigger values in there. So put in 10, then put in 100, then put in 1,000, then 1,000,000, then 1,000,000,000, then 1,000,000,000. And you'll see that this number keeps getting closer and closer and closer to this. And as you get to the actual limit, as you get actually to infinity, it becomes equal to e. I can show you that real quick here. Let's just look at 1 plus 1 over n to the power of n when n equals 1. We get 1 plus 1 over 1 to the power of 1. On the inside, that's 1 plus 2. Or sorry, 1 plus 1 is 2. 2 to the power of 1 is 2. When n equals 10, we get 1 plus 1 over 10 to the power of 10. This one I'll use a calculator for. 1 plus 1 over 10 is just 1.1. So 1.1 to the power of 10 is 2.5937. If you plug in 100 into here, we get 1.01 to the power of 100, 2.7048. continues on. And then if you plug in, I'm just going to do something big like 1 million. Just to kind of save some time here. And to the power of 1 million, I'm getting 2.718280469. You see, it's not the exact same, 2.71828, right? That's the same thing as here, 2.71828. But then we have 0469, and this course continues on. And this is 1827. So it's close, but it's not quite there. If you just kept trying bigger and bigger numbers, you get a better and better approximation for E. So this number might seem a little weird, and you may not know why it's so useful. It's used very frequently in mathematics. It's actually it's used a lot in applications like physics and other things like that. But one of the most useful things is when you're talking about continuously compounding things, be it like populations. It could be money, but money doesn't typically continuously compound. Populations is probably the best example of it. Also, radioactive decay, that also is a continuous thing. And there's a formula for that. Very simple, and that's because it all relies on the power of E. So this models continuously compounding growth or decay. So you have, this is the amount after a certain period of time with a certain growth rate and a starting amount. This is the starting amount. This is the time it takes to grow. This is the rate of growth. And the A is, of course, the ending amount. And E is our number that we know. E should be in calculators, as a given value in the calculator, just like pi is given on calculators. That's because both of them are used very frequently. Now, this is for continuously compounding things. Not everything continuously compounds. Like money, for instance. Money, like banks will typically compound interest maybe daily, monthly, bi-monthly, quarterly, maybe yearly. And that you can't use this formula for that. This is a continuously compounding thing. We have a different formula for that. And that is A equals P 1 plus R over N to the NT. It's very similar. You see here that the base is what's changing here, right? 1 plus Rn is now the base instead of E. But we have the same kind of ideas. P is the starting amount, A is the ending amount, T is time, and the rate, right? That's the same thing as this R here. N is how often the whatever the thing is you're talking about. Most likely money is what you're talking about, but how often it is compounded. And really, compounding is just saying how often do you add the interest back onto the actual amount. It's hard to think about without talking about a specific example, like money, for instance. Just to kind of keep it in mind, if we have $1,000 in a savings account and our account gave us 10% interest and it compounded once a year, so it compounded once per year, then that means after 1 year, you gain 10% interest and it's added onto the principal, the amount that you're getting, that you started with. So after 1 year, we would gain $100. That's because 10% of 1,000 is 100. Now, for the second year, we don't have $1,000. Now we have $1,100. And so now we're taking 10% of this once per year, and that gives us $110. Now we start the third year with 121.10, and so on and so forth. We keep compounding. So the compounding, how often it compounds, is when you put this into the new principal and you have a new starting amount. Hopefully that makes sense. Typically, you won't see growth very fast unless you have a very high growth rate, right? If this was like 200%, then you'd see it compounding incredibly fast. But most of the times, like for banks and things like that, you see interest rates of like 3% or maybe like 2.5%, something like that. And the growth is going to take a very long time before you start seeing some stuff. Like after a year or two, you're not going to see that much change. Compounding interest really shows its strength in the long run. The question is, after 30 years, what do you have in this? You'd have a way, way more than just $1,000. You can figure out how much you would have by just using this formula. I want to show you that here. So let's look at a situation. Suppose we have $13,000 to invest. That 3 over again. $13,000 is being invested, and it's saying which account yields more money after 2 years. So this is after 2 years. We have 6% interest rate for both of the accounts, and the first account is compounded daily. The second account is compounded continuously. Continuously. So which one has more after 2 years? Well, compounding daily, we're going to use our first formula. E times 1 plus r over n to the nt. And compounding continuously gives us p, it's APERT for short. Okay, so our starting principal, that's what the P stands for, it stands for principal, is our starting amount, which is 13,000. And plus the rate is 6%, so that you use as a decimal. And compounding daily, so a daily compounding is how many times per year, since we're talking about years here, right? We're talking about 2 years. So how much is this per year? Well, you can use as an average like 364 days per year or 365, whichever one you want to use. 365 is what I want to use. So that's what n is. N is how often does it compound per year. So in this case, it compounds 365 times a year. And how many years is it going to go for? It's going to go for 2 years. This one's simpler. 13,000 times e to the power of 0.06 times 2. Of course, you're going to want to use a calculator for this. It's really not doable by hand. It would take a long time to do it by hand, so don't do it. 2. For this first one, I get 14,657. And this is a dollar amount, so I'm rounding to 2 decimal places. The next one, .06 times 2 gives us 14,657.46. And you see the difference is a mere 15 cents. But the continuously compounding interest is more. That's because continuously compounding compounds more often than the daily compounding. Daily is pretty close to continuous, so it's not terribly, as you can see, 15 cents is not that big of a difference. But if this were in for like 1,000 years, that 15 cents would be a huge difference. So continuously compounding is more desirable, but you're never going to find that in a bank. Daily is probably the most you'll see compounded, so that's probably the best you're going to get. Now, as you see here, after 2 years, the account gained about 1650. So like we gained about 16. Well, we gained about $1,657 in both accounts, which is a fair amount, right? $1,000 is nothing to be scoffed at. But where do you see the real growth? Is asking, what's it going to be 30 years from now? If we were to look at this thing 30 years from now, so instead we're looking at t equal to 30. I'm going to do the same thing for this compounding here. So all I'm doing here is I'm replacing the 2 with 30. Now let's see what number we get. So for the first one, it's $78,633. And for the next one, I get $78,645.42. So now you see that we have way more than doubled our growth. I mean, I can do that real quick. The rough estimate, it's about 6 times the growth. So we've multiplied our principal by 6, and we didn't do anything. We just put money in a bank at a certain interest rate. And now you can see here, the difference between these two is about $12. Again, not a whole lot for these dollar amounts, but like I said, put it in there for 1,000 years, and you're going to see a big difference between them. Of course, the numbers are going to be huge. Like I'm guessing like billions of dollars or whatever. You can do that by just plugging in 1,000 into here, which you should try on your own. But that's the power of compounding interest. It's over the long haul, not the short term. Okay, the last thing we'll talk about in this video is this problem here. This model is inflation. Today's value of the dollar C, so that this is the dollar amount here. This is today's dollar amount. After T years, with inflation rate R. Inflation rate R is going to be worth S dollars after T years. So this is not, again, a dollar amount. So we expect this number to increase. So let's look at this problem here. What is a $73,000 home worth in 23 years if we have an inflation rate of 7%? So our current dollar worth for a home is $73,000. So that's what C is going to be. R is the inflation rate of 7%, and we have 23 years. Now let's actually calculate that. Plugging this in a calculator, we get 0.07 to the power of 23. We get 346,058. $346,000 and $346,000 pretty much.